So here we can start with our topic DIF-FFT, standing for decimation in frequency fast Fourier transformation here. So as fast Fourier transformation, whether you take decimation in time or decimation in frequency, is having the discrete Fourier transformation operation here that we abbreviate at the DFT here. So let us first of all have the recall to the definition of DFT. Here the DFT for the discrete time sequence x of n can be expressed into the form. In general, x of k can also be taken. So here the capital casing is used here. So we have capital X of k computed as the summation n is equal to 0 to capital N minus 1 over x of n multiplied to w suffix capital N and to the power we have small k into small n. Whereas the small k value holds from 0, 1 to up to capital N minus 1 for the n point DFT here. So in this representation, the W stands for the twiddle factor here. So the twiddle factor in general can be represented capital W suffix n. So n can be in general 2 value, 4 value, 8 value, 16 value. This way we can have W suffix 2, W suffix 4, W suffix 8, W suffix 16. So these many type of the twiddle factors we can work with to obtain that particular point of DFT operation here. So W suffix n is equal to e to the power minus j times 2 pi by capital N here. Now the above expression that we have represented for the DFT obtained as capital X of k can be represented into its expanded form as like we first of all mention small x of 0, we add it with x of 1 multiplied by the twiddle factor here w suffix capital N and the power is simply small k. In this fashion, if we go on adding up to x of n minus 1 multiplied to the twiddle factor form w suffix capital N and to the power we have k in the bracket n minus 1. So this is the complete representation into the expanded form here. Now upon having the splitting of this expanded form into the three parts, we can express capital X of k by this equation. So first of all we mention x of 0 added to x of 1 multiplied by w suffix n and the power k. Next to that we split it with x of capital N by 2 minus 1 multiplied to the twiddle w suffix n, the power is k in the bracket n by 2 minus 1, further added to x of n by 2 multiplied by w to the power k times capital N by 2. And lastly the third part can be shown as here we have x of n minus 1 multiplied to the twiddle w suffix capital N to the power here we have k in the bracket capital N minus 1 here. So with this splitted representation for the discrete Fourier transform capital X of k, we can rewrite the summation like this. So here we make the two terms onto the right hand side where we have capital X of k first of all by the summation where we have n is equal to 0 to capital N by 2 minus 1 operated over x of n multiplied by the twiddle factor w suffix capital N, the power is k into n here. The second term which is added to it is here we have the summation small n that starts from n by 2 capital N by 2 up to capital N minus 1, the latter part here, operated for x of n multiplied to the twiddle capital W by capital W into the suffix, here we have k into n here. Now the modification of the latter part, that it is the second part onto the right hand side, gives us the new representation here. So we keep left hand side x of k as it is. The first term, the summation n is equal to 0 to capital N by 2 minus 1 operated over x of n into the twiddle w suffix capital N, the power is k into small n. Here the second term is represented First of all, w suffix capital N to the power n by 2 into k, whereas it is in multiplication to the summation where we have small n is equal to 0 to capital N by 2 minus 1 operated over x of n plus capital N by 2 into the twiddle we have w suffix capital N, and the power here we have small k into small n here. Now along with this modification into the second part here, we use the notation that has already been represented, that is the twiddle capital W suffix capital N to the power capital N by 2 here. So this is nothing but e to the power minus j times 2 pi in multiplication to the ratio n by 2, which is completely divided by capital N here. So capital N can be cancelled out from the numerator denominator, 2 is also getting cancelled. So here we shall be left with e to the power minus j times pi, which will result into the value minus 1 here. Now with this the twiddle representation, we get the final form of the representation for the discrete Fourier transformation capital X of k, that is equal to the summation small n is equal to 0 to capital N by 2 minus 1 operated over x of n, which is added to minus 1 to the power k into x of n plus capital N by 2. The bracket is completed, and here it is in the multiplication to capital W suffix capital N k n here. Now let us have the substitution of small k is equal to twice m as the even number of achieves here. We can have capital X as a function of twice m. Here it is the change made. In place of small k, we let twice m here. So this gives us to the form summation n is equal to 0 to capital N by 2 minus 1 over x of n added to n plus here capital N by 2 here. In multiplication to, here we have the W suffix capital N to the power twice of m into small n, here it is. Now while we have the substitution of another type for the k, if we make twice m plus 1, so the previous case that it was for the even, now this will be the case for odd number here. So this yields the capital X as a function of twice m plus 1 computed as the summation n is equal to 0 to capital N by 2 minus 1 operated over x of n minus x of n plus capital N by 2 in multiplication to the twiddle capital W suffix capital N n to the power another twiddle, here we have capital W suffix capital N to the power twice of small m into small n. So along with this representation, if we make the use of the twiddle, here we have capital W, the suffix capital N as usual, and the power if it is 2. So that time we have the exponential e to the power minus j 2 pi into 2 divided by capital N. So that can be of the form e to the power minus j 2 pi by capital N by 2, which will result into capital W suffix capital N by 2 here. So this is the most important relation to convert this twiddle into this particular form, that gives capital X of twice m to the form where we write the summation n is equal to 0 to capital N by 2 minus 1 operated over small a of n multiplied to the twiddle. Here we have W suffix capital N by 2 to the power small m small n, here it is. So this is nothing but the DFT operated over the a of n with capital N by 2 points, that it means half of the points here. Along with this representation, capital X of twice m plus 1 when computed, we have it to the form the summation small n is equal to 0 to capital N by 2 minus 1 operated over b of n in multiplication to the two twiddles. Here we have capital W suffix n the power small n here. The second twiddle W suffix capital N by 2 the power m into n. So this is nothing but the DFT of b of n, the twiddle W suffix n into small n in the power in multiplication to b of n. So this is again with half of the points, that is capital N by 2 points here. So in both of these representations for capital X of twice m plus 1 and capital X of twice m in the previous case, we have small a of n and small b of n introduced and expressed by the following mathematical expressions. So a of n, first of all, it is equal to x of n added to x of n plus capital N by 2, for the values of small n is equal to 0, 1 and so on up to capital N by 2 minus 1. Whereas for small b of n, this is equal to x of n added to x of n plus capital N by 2 for the all values of small n, that is equal to 0, 1 and so on up to capital N by 2 minus 1 here. So from the combined representations using small a of n and b of n, the final representation for the DFT can be summarized. Here we write the DFT of x of n with capital N points. So opting DFT of a of n with half capital N by 2 points and DFT of b of n multiplied by w suffix n power small n with another half capital N by 2 points here. Now this is the technique with respect to which we call this particular fast Fourier transformation algorithm to be of decimation in frequency type here. Now the application of such algorithm to the discrete time sequence for the first iteration can be graphically represented in this particular form, where capital N is equal to 8 here. So 8 point DFT here we can call FFT. 8 point FFT can be computed for the first iteration like this. So on to the left hand side, you can see the discrete time sequence values: small x of 0, small x of 1, small x of 2, small x of 3, small x of 4, x of 5, x of 6, x of 7 arranged here. Whereas into the first iteration we come to know small a of 0, a of 1, a of 2, a of 3. Next to that we have the b, small b of 0, b of 1, b of 2, b of 3 here. Now the multiplications by positive 1, negative ones are represented here, and the b's are further operated with the help of the twiddles. Here we have capital W suffix capital N, the powers are 0, 1, here we have 2 and then 3 here. Next to that, the first 4 branches are fed to the half point DFT, that it is capital N by 2, whereas the rest of the 4 are given to another half point DFT, capital N by 2 DFT. So this results on to the right hand side after the first iteration. We have capital X of 0, capital X of 2, capital X of 6, capital X of 4, it is first of all, then 6, then capital X of 1, capital X of 3, capital X of 5, capital X of 7, which we can have the rearrangement to write down the final answer here. Now in this particular representation, there are certain graphical operations which can be defined. Here we have, as the first case, to this particular node, here we have the input from X and the input from Y. Both are the incoming arrows, so these are nothing but the additive signals here. So the resultant signal Z is nothing but the addition of the two. So Z is equal to X plus Y here. Now on to the another hand, if the branch that has been coming from the Y part, if it is multiplied by -1, so here Z should be equal to X minus Y here. Now in general, if we have W as a multiplicand here on this particular branch, so Z simply we write the resulting signal to be W multiplied to the X here. So with this representations of the graphical form, we have to make the computations for the fast Fourier transformation. So for the first iteration we have shown the result. Now the second part can be also continued here. Hence the second iteration for the same 8 point fast Fourier transformation FFT can be continued in this manner here. So now here we have, after the first iteration, the second iteration is again having the computation where we again make half points. So out of capital N by 2, here we make capital N by 4 DFTs applicable to the sequences manipulated with small a of n's here, whereas capital N by 4 point DFTs we make the computations with the help of the twiddles w suffix capital N to the power 0 and 2 here. Whereas for the latter half, again we have the split up into n by 4 DFTs again with the use of the twiddles here. So finally here we obtain capital X of 0, capital X of 4, capital X of 2, capital X of 6, capital X of 1, capital X of 5, capital X of 3, capital X of 7 here. So this way, if you have the comparison to the earlier representation here, the positions of the samples onto the right hand side has been changed with the application of the second type of the iteration here. Now in general, the block diagram representation for the 8-point fast Fourier transformation having the total 12 multiplications can be shown in this particular form. So here we have the inputs are the same, that it is x of 0 small casing, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6, x of 7. So onto the output side, here we have capital X of 0, capital X of 4, capital X of 2, capital X of 6, capital X of 1, capital X of 5, capital X of 3, capital X of 7 here. Now upon having the bit reversal processes into this fast Fourier transformation, the tabulation is very informative. So here we have the first column representing the binary combinations as like 000, 001, 010, 011, 100, 101, 110, 111, having the relation to the indexes to 0, 1, 2, 3, 4, 5, 6 and 7 into the respective manner here. Whereas the first split here we make and arrange them as 0, 2, 4, 6. At the second split we take 0, 4 and then the left one 2, 6 here. At the third split we take 0, the 4, the 2, the 6 here. So the bit reversal here you can see at the output we have 000, 100 corresponding to the 4, 010 to the 2, 011 to the 6 here. On to the latter half also we have here 1, 3, 5, 7. Into the second split we have 1, 5 and 3, 7 here. Whereas into the third split we have 1 by 001, 5 by 101, 3 by 011 and 7 by 111 here. So this is what the bit reversal process is employed into the fast Fourier transformation algorithm here. The block diagram for the inverse of the 8-point FFT to get back the details of the discrete time sequence small x of n can also be shown here by the use of this DIF-FFT here. So for the inverse case we have this butterfly diagram. So this is what the DIF-FFT we have discussed so far.